I think that we will have another few people joining as we start the meeting. So just to let you know, this meeting will be recorded. Thank you very much, everyone, for joining us today. I'm Aurora Maccarone, and I'm an associate professor based at Heriot-Watt University. And along with Lucy, we are and Akil. We have organized, in collaboration with the QuSIT and QEPNT Hubs, this session of online seminars. And today we have Alex Clark, who will talk about telecommunication-band quantum technologies for networking, sensing, and ranging. So Alex is an associate professor in quantum technologies at the University of Bristol. He is the director of the Quantum Engineering Technology Laboratories, which is a 100 people interdisciplinary research center. And he's an investigator and a work package co-leader in 3 quantum technology hubs, QuSIT and QEPNT and IQN. So his research focuses on hybrid quantum devices, including solid-state single photon sources, atomic quantum memories, and integrated nonlinear nanophotonics, all of which he applies to quantum computing, communication, sensing, and imaging. So if you, before handing over to Alex, if you have any question, please use the question and answer section here on Teams. But then also Alex will let you know when it's time to ask questions, and he will have a look at the section. So Alex, thank you very much for joining us today, and I will hand it over to you.
Brilliant. Thank you very much, Aurora. Yeah, it's a pleasure to be asked to give one of these seminars. And as Aurora mentioned, I have a kind of intimate relationship with these quantum hubs, and I'm very excited to tell you about different types of research that I'm doing within the hubs under the umbrella that a lot of them are using these telecommunication-band devices in order to leverage off-the-shelf components and kind of cheaper, more scalable and more available devices for building these kinds of quantum technologies. So let's get started. Just a little bit about the Quantum Engineering Technology Labs before I dive into my research mainly. There's 12 group leaders currently in quantum technologies in KET Labs. This includes myself working on the areas that Aurora already mentioned, and a picture here just displays some of the organic molecule photon sources that I work on. Anthony Lang's group deals with quantum simulation, mainly in integrated photonic devices, and their use towards quantum computing. And he also has a spin-out company here in Bristol, Duality Quantum Photonics. John Rarity, a lot of you may know, a fellow of the Royal Society, a pioneer of quantum optics, and is still performing pioneering experiments today. Ruth Alton works on quantum dots and integrating quantum dots into nanophotonic devices with a good view towards controlling the electron spin in the quantum dot and how they relate to the local nuclear spins. Krishna Balaram's group works on suspended nanophotonic devices, especially targeting piezoelectric or Chi2 active materials, which will allow the launching of sound waves via the injection of microwave photons into a device, which can then modulate an optical device. So you can then have a link between the microwave spectrum and the optical spectrum via sound in an integrated photonic device. And you could use this for building something like a microwave to optical transduction device, which could link together future quantum computers. Rachel Clark works on integrating detectors and devices into silicon nitride that can be used for continuous variable quantum information experiments, including the generation and detection of squeeze light. Siddharth Joshi works on quantum communication, especially on fiber-based multi-user communication networks and entanglement distribution, and more recently on satellite-based quantum key distribution, including the recent satellite that was launched by the Quantum Communications Hub and Integrated Quantum Networks Hub just last month, SPOC. Julia Rubino's group works on the interface between quantum theory, quantum foundations, and integrated photonics to test those foundational theories. And so really the ideas that have come up from a theoretical point of view can be immediately tested in the lab in these exquisite devices that can be integrated on chip. Edmund Harbord's group works on quantum dots and quantum well lasers, lasers for quantum technologies as well. Andrew Young's group works on enhancing the collection of photons from integrated micropillar quantum dots, especially using direct write methods. Carrie Widener's group works on atomic physics and trapping and manipulating atoms for building quantum technologies, including inertial sensors in the QEPNT, the Quantum-Enabled Position, Navigation and Timing Hub. And John Goldwyn just recently joined us here in Bristol as the Director of the Quantum Information Science and Technology, CDT, and John works on atomic physics and quantum optics, especially around quantum computing and cavity QED. So an exciting team of people, all with their own research groups or with their own research ideas, but all coming together under this interdisciplinary research center that I run, the Quantum Engineering Technology Labs. So a bit more on my group, just before we go into the kind of quantum technologies I'm going to discuss today. My group works on molecular interactions with phonons, photons, and electrons, really targeting using single molecules, such as this dibenzotyrrolene molecule that you can see on your screen, as a single photon source that can be fully solid state and scalable. In order to have a very good photon source, you don't just want the molecule or the single emitter in the solid state to be emitting nice photons. It has to be emitting them into a well-known optical mode. And in order to engineer the emitter to emit those photons into a direction and a mode that you know, then the best way to do that is to couple the single molecule to a nanophotonic device. In this case, I've shown a waveguide, but this could also be a cavity, bullseye structures, lenses, many different structures that we're testing here. We also have a recently funded project through a joint project with Jonathan Hood's group in Purdue in the US, funded by NSF and UKRI. And that's to look at these single molecules, but not only use them as single photon sources, but use light to be able to control the electron spin inside the single molecule. So build a spin photon interface based on these all organic molecules. And that's an exciting prospect for the future. Down to the kind of quantum hub activities that I'm involved in. So in Quantic and now in QuSIT, the Quantum Sensing, Imaging and Timing Hub, I work on nonlinear devices for quantum imaging and for frequency conversion. And I will tell you some more about those kind of experiments today, especially targeting gas sensing using a process called nonlinear interferometry. In the Integrated Quantum Networks Hub, kind of fed by a pre-project with the Quantum Computing and Simulation Hub, I work on interfacing single molecules with atomic quantum memories. And I'm going to tell you about one type of quantum memory today that accesses telecommunication-band telecommunication wavelength photons. And then in the Quantum-Enabled Position and Navigation and Timing Hub, QEPNT, my group works on covert range-finding systems based on telecommunication-band lasers that can be randomly modulated both in time and in wavelength. And this has allowed us to do field trials of imaging of buildings across Bristol. And I will tell you more about that today as well. So then just an overview for the kind of areas that we're going to talk about for the specific quantum technologies today. I've called it the triple threat, the 3 quantum hubs. So you're going to have to sit through 3 quantum hubs worth of work. But I hope you find it all interesting. We'll talk about these ladder-based quantum memories, which we're working on in the Integrated Quantum Networks Hub, which, as you can see, access both the Telecom C-band and the Telecom O-band. We'll talk about this range-finding experiments that we've been doing using telecommunication-band photons from a pulsed laser and single photon detectors. And I'll tell you about the work in the Quantum Sensing, Imaging and Timing Hub of doing imaging at longer wavelengths and only detecting visible light, and our integration of those effects into integrated photonic devices at the very end. So I think after each section, I will also give a chance, if anybody has any burning questions, to be able to ask them about that section. And at the end, I will also have more time if you want to ask your questions at the end as well. As Aurora mentioned, you can put them in the Q&A. So let's start off with the work in the Integrated Quantum Networks Hub. So in the IQN Hub, the quantum memory work package 1 of the hub, is split across a number of different types of quantum memory, and those range from solid state ensembles through to trapped ions, through to atomic vapors. And this is ensembles of atoms that are in free space. My group is part of the atomic vapor team, so in the University of Bristol, and we're collaborating, well, the other group members are those at the University of Southampton in Patrick Ledium's group, and those at the University of Oxford, so Sarah Thomas and Ian Walmsley, who are working there. The ambition of this part of the hub is to be able to entangle atomic vapor memories across long distance scales, national distance scales. And to be able to do that, we need a high efficiency memory, needs to be low noise, needs to be long-lived, preferably because we want to communicate over optical fiber. It wants to be telecommunication wavelength compatible and have a bandwidth that's compatible with transmitting over these kinds of distances and being able to repeat our experiments quickly. And in an ideal world, this type of quantum memory would also be portable and scalable. So we have a lot of things that we need to tick off. It turns out that there are some memory protocols in these atomic vapors that can hit a number of these simultaneously, and I'll talk about what we need to hit to be able to do these kind of experiments. A dream for us is really not only to take the quantum memories across the network, but to have the photons required to interface with the quantum memories so that we can entangle quantum memories at a distance. We can do that either by generating single photons, and here's some examples of some different single photon emitters that we're looking at. So single rare earth ions embedded in molecules, all organic molecules like the dibenzotyrrolene molecule that I already mentioned, or even interstitial defects in solid state materials. In this case, this is a G center in silicon that emits at telecommunication wavelengths. Alternatively, you could also generate entangled photons or pairs of photons that can be correlated and generated by nonlinear optical processes. These could use bulk crystals, like these periodically poled lithium niobate crystals from cohesion, or we can use integrated photonic devices such as these silicon nitride nanophotonic chips that were fabricated by Cornerstone in Southampton. After we've generated photons, we can distribute them through a network using beam splitters, for example, and detect them in order to know whether the photons came from one place or another. If we place memories at different nodes of this parts of this network, then we can entangle those memories together, and we can hold on to that entanglement until we read it out from the memory. However, a lot of these single photon sources tend to generate photons at visible wavelengths. Not all of them, or the best photon sources generate visible wavelengths. And to distribute these over long distances, we also want some kind of single photon frequency conversion that can take us to the telecommunication. Right. So what are we trying to do in the Integrated Quantum Network Hub in order to build these kinds of memories? The first memory that we have been targeting is an Ott-the-Town split quantum memory, which looks a bit like a Raman quantum memory. However, in this case, we're using the two ground states in rubidium and linking them via a single excited state with one laser and one photon, where you can think about this like two optical signals, one of which can be weak. When we do this, then we can bring in a photon and we can build up a coherence between the two ground states. And this means one atom out of an ensemble has been pushed over into another ground state, and we don't know which atom it is, and so they're in what we call a spin wave. They're in a coherent superposition of one of the atoms having absorbed a single photon. By bringing in a pulse of light at later time, we're able to bring the photon back out efficiently. But in this case, this didn't access the telecommunication bands, but it does provide a long-lived quantum memory because these ground states have a long lifetime, and especially in cold atoms where the atoms are not moving. But today's talk is going to be more about accessing those telecommunication band wavelengths. And so another quantum memory protocol, which is based on a ladder transition, is something called off-resonant cascaded absorption that was developed by University of Oxford, and then Orca, the company, which spun out from there, and people who worked at Imperial in the meantime from the same group of Ian Walmsley. The idea here is instead of using two ground states, you use one ground state and one higher excited state as your ground state and your storage state. This means instead of having your lasers come up and down, both lasers are going up, and you're taking a single atom from this ground state via an intermediate state to an excited state. Again, you don't know which atom in the cloud has been excited after any single photon has come in with a pulse of light. And because you don't know which, then you're in a large superposition of one of the atoms having absorbed a photon. As long as the atoms don't move too much, then it means that you can then send in a pulse of light later, and you can bring your photon back out. However, you have to bear in mind that this is an excited state now, and so it could spontaneously decay back to the ground state or to an intermediate state. And that means you have to read out your photon before that spontaneous decay has possibly happened. So let's just look at this a bit more diagrammatically, this off-resonant cascaded absorption in this highly non-degenerate regime, where in this case, this is a rubidium atom, and we're using 780 nanometers on the normal D2 line between the 5s1/2 and the 5p3/2 state. And then we're going from the 5p3/2 state to the 4d5/2 state, which happens to be a telecommunication band wavelength, 1530 nanometers, so in the telecommunication C-band. I guess as an aside, for those of you that don't know, this is typically a telecommunication wavelength because it's the lowest wavelength that you'll see in silica fiber. And this means that all the glass fiber that makes the internet all around us can be used for distributing these wavelengths efficiently with lower loss. So it's nice to have photons that sit at these wavelengths. So what do? We bring in a photon and we bring in a pulse of light, and we store that photon in one of the atoms in the cloud. In this case, I deliberately drew that we wrote in a 780 nanometer photon with a telecom laser pulse. We could use the same color laser pulse to bring the photon back out at the same wavelength, but actually another advantage that we're exploring with these kind of off-resonant cascaded absorption memories is whether we can use those as an efficient frequency converter as well. And I mentioned that frequency conversion is also a key component if you want to build a large-scale quantum network. So actually, instead of sending in a telecom laser pulse, we could wait after a short time and bring in the laser pulse at the 780 nanometer wavelength. And if we do that, we can bring out the single photon at the 1530 nanometers. And this has been efficiently simulated by my previous student, Paul Burdekin, who's now a postdoc working in Sarah Thomas and Ian Wolsey's team in Oxford. So we're working on that at the moment. However, if you choose to just bring out your light at actually in either case, if you choose to only use these 3 levels in this off-resonant cascaded absorption scheme, then there's a problem. When a single photon is absorbed at one of the wavelengths, then there's a momentum kick to the atom, and the momentum kick is proportional to the energy carried by the photon. So because a photon must be absorbed from the laser pulse, and the photon that you want to store is also absorbed, then it means there's a mismatch in the amount of energy that's absorbed, and we send these in counter-propagating to one another. But the momentum mismatch from using these different wavelengths, these different energies, is not completely cancelled, and that means that this excess momentum causes a dephasing in the system. That means that actually, because the atoms are also slightly moving, we can't read out the memory fast enough to be able to have a low decoherence in the system. And what that means is we have a limited memory lifetime. So there's some extremely impressive experiments that were done by Sarah Thomas's group to demonstrate this off-resonant cascaded absorption process and to demonstrate its use as a quantum memory. You can see this with Sarah, Ian, and Patrick on the paper here. So this was published in PhysRev Applied just a few years ago. And this is their input signal. And then this is the output signal that they see. But if you look on the time axis here, you'll see that this is only this is around a nanosecond. And so the storage time is really limited in this case by this momentum mismatch that's present in the system where you have 2 very different wavelengths of light. This was with attenuated coherent states. And later on, a year later, they also showed that you could take photons from a quantum dot and be able to also store those photons from a quantum dot and retrieve them. But again, the same problem arises in that you're limited in only a nanosecond or so of storage time before the whole system is dephased and you can't bring the photon out efficiently anymore. And so how can we get around that? Well, one way that we're exploring to get around that is actually to bring in a fourth level into the system. So by having another transition that takes us from the 4D 5/2 state to the 4F 7/2 state, it turns out that this actually is also a telecommunication band compatible transition, in this case at 1344 nanometers, which is the telecom O band. Again, an aside, but the O band is called the original band. It's actually closer to the zero dispersion wavelength of the silica fiber that we use in the internet. However, it's a bit more lossy than 50 nanometers, which is the center of the C band. So people tend to not use the O band as much anymore. But yeah, O band stands for original. So what happens if we use these 4 levels instead of only 3 levels? So we now have 3 lasers. If we have our 780 nanometer photon that comes in, then the previous case of the momentum mismatch of only bringing in the 1530 nanometer photon is huge. So these are representing the K vectors of the absorption of the light. But if we now bring in this 1344 nanometer light in the same direction as the 1530 nanometer light, then it means that we've almost cancelled the momentum completely. Actually, by putting a small angle between these, we're able to completely cancel the momentum. So the light has to come in at slightly different angles. So what does that look like? Well, the photon comes in and 2 pulses come in at slightly different angles to the input 780 nanometer photon. This allows full cancellation of that momentum. And also, we're currently working on simulations to prove that we can have frequency conversion between any of these wavelengths. So this will be a multi-wavelength frequency converter that also acts as a quantum memory. So this is something that we're currently exploring. So what are we doing in the lab? Well, in a previous QCS Hub Partnership resource-funded project, we demonstrated that we could do spectroscopy of these higher lying transitions by using a 780 nanometer laser and a 1529 nanometer laser. When you do this, if you send through a weak 780 nanometer laser and you scan the wavelength of a stronger 1529 nanometer probe, then you're able to modulate the transmission of the 780 nanometer light. And this is due to something called double resonance optical pumping in the system, or drop. So if we look at the output photodiode here, we're able to see a signal that comes through the system at 780 nanometers as we tune the 1529 nanometer laser. So we're proving that we can get our lasers aligned to these transitions in the rubidium. Because you have independent control of the wavelength of both the 780 and the 1529 nanometer laser, then it means that you can adjust the wavelength of the lasers independently, because you now have 2 detunings of the lasers from the resonances in the rubidium. This system here, you can see we're tuning the 780 nanometer laser this way, and we're monitoring the output on what's called a polarization spectroscopy system. So we're actually setting it so that the light passing through the cell is circularly polarized, and we're looking at the difference between 2 polarizations on the output of the cell for a probe beam. And we're able to use this just to check that our 780 nanometer laser is scanning the same as we move the 1529 nanometer laser, but that's not affecting this normal spectroscopy. Now, if we overlap the 780 and the 1529 nanometer beams in the rubidium vapor cell, then what we can see is as we change the wavelength of the 780 nanometer laser, we can compensate the wavelength of the 1529 nanometer laser and always observe these drop features as these diagonal stripes in a dual laser drop spectrum. So this is something that's recently been shown by Isa Ali, a PhD student in my group. And these match very well to his simulations of what you would expect from sending these lasers into the rubidium, taking into account all of the levels in the rubidium. And in this case, this is for rubidium 87. What we then also found was instead of detecting the 780 nanometer output, we could also detect the 1529 nanometer output. And rather than detect it directly, we decided to see if we could do a similar trick to the polarization spectroscopy, where we send through a circularly polarized pump beam at 780 nanometers, and that changes the absorption of the different polarizations of the 1529 nanometer light that passes through the same cell. by adjusting a half-wave plate to balance the detection of horizontal and vertical light at the outputs of a polarizing beam splitter, we can look at the differential absorption that you see for these two different polarizations, and this can give us what's called a polarization locking signal. So these are the typical signals that we would see as we adjust the detuning of our laser. And what we see on the output there is that you can see that the vertical and horizontal detections are different to one another. They exist at different detunings. If we subtract one from the other, then we end up with this nice, what we call dispersive locking signal that passes through zero in terms of the difference between the photodiode signals. And that's very good for locking these lasers close to the resonances that are needed to be able to perform the quantum memory operations. So we then did a similar, well, took the same setup as we had last time, but now we're detecting the outputs here instead of detecting the output from the of the 780 nanometer light. We're detecting the 1529 nanometer light. Once again, we can do this polarization spectroscopy, and now I'm showing you the polarization spectroscopy for the rubidium 85 and rubidium 87 in the same image. If we look at the output A, so detector A on the polarization output, this is like the vertical output of the beam splitter, then we see these kind of absorption signals. And if we look on the other detector, then we see some more absorption signals. They look very similar, but actually they're occurring at different detunings to one another. And if we subtract one signal from the other, then you'll see that we go from something that goes through positive and negative signals with an offset here, but you can see that it goes up and down. So you've got a light stripe and a dark stripe, which means you're running through an average in between those two. So this shows that we can do this dual laser spectroscopy in doing this, an optical rotation, but with this ladder transitions in the rubidium, which allows us to then lock the lasers for the memories that we're working on. Another thing I wanted to mention that we've been developing over the last year or so of working in the hub is a portable magneto-optical trap system that's going to be used for doing cold atom type quantum memories, where you can have an extended lifetime of the quantum memories that use the ground state. And here's an example of the setup that we designed, where it's a back-to-back vacuum cells. One vacuum cell is used to make a two-dimensional magneto-optical trap, which then gets pushed via a push beam to form a three-dimensional magneto-optical trap in another vacuum cell. Here you can see the setup. This is the three-dimensional magneto-optical trap cell on this side with circular coils. This is the two-dimensional magneto-optical trap cell viewed from the end. Here's the view from the side. And down the middle, you can see that there's a hole there, and that's where we push the atoms through from one cell to another using the push beam. So yeah, watch this space. We're going to be setting up the quantum memory beam soon and getting this up and running. So that's what I wanted to tell you about targeting telecommunication band transitions in the integrated quantum networks hub. I mentioned that I would also allow, if there's any questions in between each section, I'm very happy to answer them. If you want to put them in, let me enlarge the screen here so I can have a look at the Q&A. Aurora, did you want to pick anything out, or is it okay?
At the moment, there are no questions in the section. So it's,
okay.
If anyone has any question for Alex, wants to ask directly.
So my question related to this telecom wavelength underwater quantum communication. Is it possible? How it differs in terms of experimental setup? Any specific photonics optical devices are required to establish a dedicated communication at telecom wavelength underwater?
Yeah, very interesting. Actually, underwater, if you wanted to use telecommunication wavelength, you'd be better using optical fiber. Aurora knows a lot more about this than I do, but I believe it's around the kind of green wavelength of the spectrum is the lowest loss underwater transmission that you'll get because of the particle scattering that's in the water. So actually, if you want to do communication underwater, then you'd be better off using visible wavelengths of light, not these telecommunication wavelengths.
Sorry. Which wavelength I can use?
Green, so around 500-ish nanometers.
500 nanometer. That is green. Okay.
532 is a very typical laser wavelength. So a lot of people would pick this wavelength just because it's readily available. Yeah.
Any such research is going on there at your end, underwater?
That is a very good question. Not to my knowledge. However, there could be some research that could be happening.
I'm interested if remotely any option there in simulation based research to collaborate. Faculty in a university here in India. So collaboratively, I would be happy if somebody there.
I think
such opportunity simulation based study. Yeah.
Yeah. I think from a quantum communication point of view, you can drop me an email after this and I can point you into the direction of people in the Integrated Quantum Networks Hub that may be interested in that.
Yeah, great. Definitely. Okay. I would be happy to collaborate and work together remotely.
Okay, thank you, Vishal. Thank you for your comment. I think there was one other question in the chat from Ali about some more details about the simulations, if possible. Sure. These simulations are simulations of the Maxwell block equations, although a lot of the time we can simplify the Maxwell block equations into rate equations if we take out the coherences, which makes it quicker to run, especially when we're using the full manifold of states in the rubidium in order to do the simulations. So some of the simulation results are from rate equation models, which are just solving differential equations. And if we need to take into account coherences, then we solve the full manifold of Maxwell block equations. I hope that helps you, Ali, for your question. Great. In that case, I think I'm going to continue with the next section of the talk, if that's okay with you, Aurora.
Yeah, that will be great. Thank you.
Perfect. Very good. Okay, so the next section that I wanted to tell you about was using telecommunication-band light in order to perform range finding in the and that work is funded by the Quantum-Enabled Position, Navigation and Timing Hub. So the question, I guess, that was asked or posed actually quite a long time ago, this is a more recent review paper, but a long time ago, people asked the question, can quantum states of light improve our ability to just say whether there is a target there or not there? So we send in some light, it hits something, it comes back to our receiver from the transmitter, and the question is there something there or not? And it's interesting. The question that was posed is, if I just send a pulse of light or a single photon even and look at the return, can I do a better job if I allow myself to use entangled states of light or different quantum states of light in the first place? So this question was kind of thought about back in 2008 by Seth Lloyd, and he showed that entangled states of light and an ideal joint measurement could improve target identification. But since then, it's very difficult to generate these kind of states of light, and it's also difficult to have any entanglement survive. But it turned out they didn't need entanglement to survive in this case. A year later, he worked with Jeffrey Shapiro, and they looked again, and they actually found that a similar advantage to the one that Seth Lloyd had found in the first place could be gained by using coherent states, as long as you have some coherence between the coherent states that you use in the first place. So it kind of felt like, well, maybe entanglement's not useful at all. Maybe quantum light's not useful for improving this sensitivity of range finding or quantum illumination. However, at the same time, it seems like Seth Lloyd was arguing with himself a lot of the time. They found that you could, by using two-mode squeezed vacuum states, so that is states of light that are generated via a process such as parametric down conversion, then you can have an improvement. Improvement's around 6 dB, but if you think about it, 6 dB improvement is only a factor of 4, and it only actually remained true from this particular squeezed vacuum source that they were considering, two-mode squeezed vacuum, if the number of photons per pulse was much less than 1. And so what that means is actually you're only getting a factor of 4 improvement, but you're usually seeing many orders of magnitude reduction in the level of light that you can generate from these spontaneous parametric down conversion processes. So although you may be getting an advantage kind of per photon detected, you're not detecting very many photons because you're not able to send very many photons in the first place. So people still went ahead, and this is some work from here at the University of Bristol, from Stefan Frick and John Rarity's group, of actually generating energy-time correlations from periodically poled KTP, potassium titanyl phosphate crystal. And this crystal is able to generate correlated photons in multiple wavelength pairs, signal and idler wavelength pairs. So when you generate a longer wavelength photon in the signal, you generate shorter wavelength photon in the idler, vice versa. But you always have correlations between these two outputs. So you can make multiple wavelength channels. However, because this is a spontaneous process of taking one laser photon and making a pair of photons, and this spontaneous process is very inefficient, it's difficult to make a large number of photon pairs per second. Because of this low brightness, it meant that the distance over which they could do a range-finding experiment was limited. So what is the range-finding experiment? Well, it turns out if you keep hold of the time when you generated one of these colors of photons, one signal photon of the pair of photons, then you're then able to send the other of the pair out to a target, and some of that will be reflected back, and you can then detect that on another set of detectors. Because you know the time that you sent each wavelength, then you can look at the time of arrival of each wavelength coming back, and you're then able to detect your distance to the target because you know what the speed of light is and you know the time that you sent the pulse. But this was limited to really being done over a few meters just because of the very low brightness of the source being used. And you can see how discretized the kind of brightness is by the fact that you have this large error in this kind of, even in the background and signal level that you detect. So we asked ourselves the question, can we engineer energy time correlations, but using bright pulsed light? So without having to use this spontaneous parametric down conversion process. And some of you might say, well, that's not quantum anymore. But I would say if you're not imaging a quantum object, you're not imaging an object that's in a superposition or has a particular phase. You're imaging a building or a person, and that person is a classical object. So all you need is the correlation. You don't need entanglement. So what did we do to engineer these energy time correlations in our system? Well, in this particular system that we built something that's able to modulate different colors at different times. So modulate, the color is the energy, the time of the modulation is what we're employing. We took a pulse laser and we spread out that pulse laser by putting it through an optical fiber that disperses the pulse laser. This is a telecommunication band, 50 nanometers. So the different wavelengths are then at different times in the output fiber. We then used an electro-optic modulator to select different parts of the pulse in order to select different telecommunication band wavelengths by changing the time that we drive the electro-optic modulator to allow the light through. We then put all those pulses back together using a compressor, which is just another dispersion controlled optical fiber or grating. And then we send that out through a transmitter. The transmitter is just an optical fiber collimator, and then we sent the light out to a building and back again. We actually sent it between two buildings in Bristol, so from the balcony of Queen's Building, an engineering building, all the way across to the Wills Memorial Building and back again. So because we know when we're applying this modulation, then when the light comes back, it comes back into this receiver after coming back from the building, so a larger lens to collect the scattered light that comes back. And we send that to a wavelength division multiplexer, an off-the-shelf system that can split up the different colors of light into different output fibers and send them to different single photon detectors. By looking at the time of arrival with a time tagger of the photons arriving at different colors and knowing when we applied the optical modulation, so which color we sent, we're able to calculate the distance between the two buildings. So this is an example of what the stretched pulse looks like. So this is what the stretched pulse in gray looks like in both time and in wavelength. And then this is us selecting out the different channels in time using the electro-optic modulator. So channel A, B, and C. And here you can see in the spectral domain, these wavelengths are all in the telecommunication bands of 1530, 1560, 1590 or so nanometers. Because this is just a laser and we're just carving a laser, we can achieve around 150 microwatts at the output of the transmitter system that sends the light out to the other building. This is around 23 million photons per pulse. So this is many orders of magnitude, 6 orders of magnitude brighter than you might be able to achieve with a spontaneous photon pair source. But it still holds energy-time correlations. So this is an example of what the return data might look like. So if we were to look at the return counts, and we look at the return counts, and we're starting our timer of our time tagger on every pulse of the 50 megahertz repetition rate laser, then we can see that there's a strong peak here, and that's a correlated peak because we're detecting the light that was sent out by us. And this is a nighttime measurement, so it has quite a low background here. If instead we correlate the data, or we start the time tagger, let's say, with the start of the random pattern of colors and times that we've applied to the system, which in this case is a long pattern repeating at 100 kilohertz repetition rate. Then what we're able to see is that we can see multiple peaks here, and these peaks would be spread out across all times, across that 100 kilohertz repetition period, so 10 microseconds. Then what we can do is we can then perform a correlation of the pattern that we applied to the electro-optic modulator and the pattern of return signals that we saw for the 3 channels. And when we do that, we end up with this plot that you can see in C here. And you can see that there's one peak that's sticking outside of all of these other peaks, and that peak corresponds to the range between the 2 buildings. Actually, it's double that plus the optical fiber, but this has been corrected for that, which is a fixed delay. By zooming, so this peak tells us about the distance that we have, and by zooming in on that single peak, what we're able to see is we can measure the distance very accurately using this system, mainly limited by the jitter of the single photon detectors, which were indium gallium arsenide APDs from ID Quantique in this case. But fitting this peak, we have around a 25 millimeter forward path maximum, and we can find the center of that peak to within a kind of millimeter of accuracy, or even sub-millimeter accuracy. So this system not only allows you to find the distance between 2 buildings, but it also improves the signal-to-noise ratio of your measurement of that distance. It turns out that the signal-to-noise ratio, it scales as your signal divided by the square root of the sum of your signal, the dark counts, and the background. But here the dark counts and the background are now divided by the number of channels that you apply for your random modulation. So the number of wavelength channels that you employ. So this means by increasing the number of wavelength channels, we can increase the signal-to-noise. In the same data that we take for our system, we're able to extract what the data would look like if we only had one wavelength operating. That's ignoring particular, or taking into account correlations between all different wavelengths. We can look at what it would be like if it was a 2 wavelength system, or as it is, a 3 wavelength modulated system. And what we're able to see is we can get an increased signal-to-noise ratio, especially in the presence of a high solar background, based on increasing the number of wavelength channels that we employ in the system. And so this is just correlation maps of the different detection channels and pattern channels that we're sending. The noise is everywhere, and the signal is picked out from that background very efficiently. So this is an example of the field trial results that we have from doing this. At night, you can see that we have the building, and we can see the range peak looks good. But actually at night, there's not so much advantage to be had in terms of signal to background. And that's just because there is not much background present at night, but we can pick out the range very efficiently. What you could do here, in fact, is to measure much more quickly. And here we've only done a 100 millisecond measurement campaign to take up this data. And we could have measured more quickly where the noise would have increased, but the 3 channels would have given an advantage. We continued and waited until the morning, and then it was rainy. So we had a day where we got all weathers within the day. So this was useful for us. The background increased, and we could still see the range very efficiently. Went through further into the afternoon, further into the morning after sunrise, and had a larger background coming from the light around us. And now you can see that you have a large background, but you can still see your peak outside the background. But as you increase the number of channels, then your signal to background, your signal remains the same, but your background is suppressed. So your signal to noise ratio is increasing. And similarly, when the sun came out, then we have an increased background even more. And we can see that we're starting to sit. The background is very high compared to our signal, but as you increase the channels that you have, you really suppress that background. So we're now working to improve the number of channels that we have. We decided to increase the distance over which we performed the range finding. We went all the way from Queen's Building over to Cabot Tower, another building in Bristol that's over 400 meters away. If we just look at the return counts in time, and we don't know the correlation is there at all, then it's very hard to pick out any correlated peak from the background. However, as soon as we do our correlation that takes into account the multiple channels and the long pattern that we've used, then we can see the range accurately, and we can see it within the background. This was done over a reasonable amount of solar background, and so what you can see is that the peak is sitting on a high background for the single channel case, but the background is once again suppressed as we increase the number of channels that we're using. We're now working to see whether we can not only that we can change this from a single pixel range finding system to a multi-pixel range finding system by using a single pixel imaging technique, where we can transmit different two-dimensional multi-mode images for our transmitter onto the target, and then have a single pixel detector on the return. So now we would also be randomly spatially modulating the signal, as well as in time and in wavelength. We also have then experiments to integrate the transmitter and take all of the fiber optic stuff from the single optical bench, integrate all of that down into a nanophotonic device. This is an indium phosphide device, and it works slightly differently to the pulse laser system that I mentioned before. The idea here is that you have a broadband continuous wave light source, which is based on a semiconductor optical amplifier that's underrun. So this is effectively just providing amplified spontaneous emission. And then you have an electro-optic modulator, a Mach-Zehnder modulator that can create pulses out from that continuous wave broadband light source. The wavelengths of that light source are then split up using an arrayed waveguide grating. So different wavelengths at telecommunication-band wavelengths are separated into different channels. And each of these are switches that can choose which wavelength gets transmitted. So we can then recombine all of the wavelengths. The transmitted wavelength gets recombined onto an amplifier, and we can amplify the light that comes out from the system. So this means that we can then turn on different wavelength channels independently. And this is currently being fabricated by Smart Photonics, a foundry in the Netherlands. This work, the fiber-based work, has recently been published in Nature Communications, so take a look if you're interested to know more about those field trials. Okay, time for another coffee sip from me. If anyone has any questions for this part of the talk, then I'm very happy to answer them. Very good. I think there is a question there I can see from Brambila. So could you elaborate for me, why do the resolution of range depend on the APD's trigger and not on the device that engineers the correlations? That's because we're engineering the pulse width of the laser that we're using is much shorter than the jitter time of the detectors that we have. So we would be limited by the generation of the pulses if we generated longer pulses, but we're generating the pulses to be of a shorter time than the jitter time of the detector. So the current jitter of the detector is the limiting factor just for us. If we had faster detectors, we could have an even better accuracy, but it turns out a millimeter accuracy over hundreds of meters is pretty good, and this is useful for many people. Is there a practical limit to scale the ranging method to more than 3 channels? Hopefully the last part of the talk showed that the integrated photonic device that we're looking at, that we're fabricating at the moment, that will have 10 channels. So the idea is to scale this up, but also miniaturize the system. So we are already doing that. Okay, good. I think in the interest of time, I think I'll move on to the next section, if that's okay with you, Aurora.
Yeah, please.
Very good. Okay. So now I'm going to switch gears out into the next hub, which is the Quantum Sensing, Imaging and Timing Hub, and tell you a bit about using these for these nonlinear optical systems for imaging at wavelengths where we don't need the detectors to work at those particular wavelengths, especially for gas sensing. So how does that process work? Well, the process that we're exploring is an equivalent to a standard Mach-Zehnder interferometer, but instead of using beam splitters in a Mach-Zehnder interferometer, where a laser comes in, it can be split to two arms and recombined on a beam splitter. If you put a phase shift in one arm of this Mach-Zehnder interferometer, then you can shift where the light comes out from the side or the bottom here. But what if we replace the beam splitter with another type of splitter? In this case, we can replace it with a parametric amplifier, a spontaneous parametric down conversion event, which can split a single pump photon into two daughter photons, a signal and an idler photon. But the difference that you can see here immediately is that here we had only one wavelength of the laser that we were using, but here the pump wavelength comes in and can generate two very different wavelengths using this splitter. So this means that actually I can generate an infrared photon, could be telecom, for example, and a visible photon from a visible pump laser. If I do the same thing as I did with a Mach-Zehnder interferometer, and I recombine those two beams onto another parametric amplifier, another spontaneous parametric down conversion event with the pump laser, then it turns out a phase shift in either arm of this interferometer can modulate whether my signal and idler photons come out of the output of this final parametric amplifier. This is good because it means I can introduce a phase shift into the long wavelength arm, or I can block the long wavelength arm, and that will modulate whether the light comes out at the short wavelength, at the visible output. So I can do infrared sensing of phase or loss by only detecting visible light. And it has some other advantages, and a lot of that is detailed in this review from Maria Chakova. So do check out that review if you're interested in this nonlinear optical interferometer. This is not a new kind of effect. It's been around for a while. It was first demonstrated with clouds of rubidium atoms via a four-wave mixing process. And in this case, they also allowed there to be injected seed beams coming into the system to do stimulated four-wave mixing. This was in Bell Labs. Later, people moved away from the atoms where all of the wavelengths for the pump, signal, and idler are very close together, limited by the spacings between the atomic levels that they were using, and moved to nonlinear crystals. And this was work from Leonard Mandel's group in Rochester, where this is a slightly different setup where the two nonlinear crystals are pumped and only one beam passes through the second crystal. In order to remove the knowledge of whether the photons were generated in the first crystal or the second crystal, they mix the signal photons on a beam splitter. And the idler is already, you have no knowledge because you don't know if this beam at the output here came from the first crystal or the second crystal. By detecting the output and modulating the position of this beam splitter, then you're able to see a modulation in phase. And this modulation could be viewed by only viewing one detector output. But again, the wavelengths were very close together in this early demonstration. In Anton Zeilinger's group, when John Rarity was visiting there, they pumped a nonlinear crystal, but in this case, they did not need two nonlinear crystals. They used the same nonlinear crystal twice in order to perform the two parametric processes needed to close the interferometer. And so this might remind you that this is a bit more like a Michelson type interferometer, or a Michelson nonlinear interferometer. Here, they could modulate the position of either the signal mirror, the idler mirror, or the pump mirror, and in all cases, they could detect on only one of the detectors whether that change in phase happened in one wavelength or another wavelength. It was detectable only on one output. However, again, at that time, all the wavelengths were very similar to one another. So a while later, In fact, about 20 years later, this same idea was revisited by Zeilinger, but with very non-degenerate wavelengths. So now they were generating 1550 nanometer telecom red beam here, and a visible 850 nanometer, detectable by a silicon detector, is what I would call it, visible, detectable by the camera in your phone, for example, yellow beam. They passed the telecom beam through an object and then put it into a second nonlinear crystal along with the pump. And by mixing those signal beams together, the one from the first crystal and the second crystal at the output, they undo the which path information, the knowledge of whether the light was generated in one crystal or another. And it turns out the absorption or phase shift of the object in the telecom beam could be seen on the output of the visible light on a simple camera. So this was the first demonstration of what they called imaging without detection. This was taken into a Michelson configuration by Leonid Kravitsky's group, by Anna Patarova in Singapore, and then was also used by Sven Ramelows' group in Berlin in order to image things like mouse brains. And here they took the wavelengths even further apart. So this one was telecom and 800 nanometers or so. This one is pumping at 660 nanometers and generating around that kind of 3 to 4 micron wavelength mid-infrared idler, and only ever detecting 800 or so, 850 nanometer light. So really they're using highly non-degenerate process here to do imaging in the mid-wave infrared without needing a mid-wave infrared detector. At Imperial College under the QuanTIC Hub, we worked on making these types of systems more compact. So this is a compact system. Green laser generates telecom and 800 nanometers. We looked at mid-infrared sensing systems. We looked at mid-infrared gas sensing here in Bristol. And we looked at seeding, balancing and loss, and also high gain systems at the time. This is the compact system built by Emma Pierce, and you can see more details about it in this paper down here. It was generating between 1.4 and 1.9 micron light, so that covers the telecommunication bands, and only detecting 740 to 850 nanometer light. We actually made this portable and took it outside the lab, took it to the Quantum Showcase here in the UK, took it all the way over to California, shipped it all the way out there and got it set up again. Emma did a great job of getting that set up, and it was working at Photonics West. And we've even had it hosted in art exhibitions in London, for example. We then made the system even more compact, down to a kind of shoebox size, and also used a quite cheap laser source, and this still worked very well at that time. How does the process work? Well, we take images at different optical delays of one of the mirrors in the interferometer, and this gives us effectively phase changes at every single pixel. If we then do a fast Fourier transform on every pixel of the image, then we're able to pick out the visibility of the nonlinear interference, the contrast of the nonlinear interference, and the phase. We can do that at different wavelengths just by changing the temperature of the nonlinear crystal that we use. So these are examples at 1550 nanometers and 1780 nanometers, only detecting light with a silicon camera, CMOS camera, just imaging this electrode here. We also found out that if you put an object into the infrared beam and you rotate that object, you can take these images at different rotation angles. If you then do a radon transformation, similar to a CT scan, then you can fully reconstruct the three-dimensional objects that you put into the infrared beam, but only detecting visible light. And there's more details of that work on the archive here from Nathan Gemmell. Some very recent work from my group here in Bristol, from Jingri Zhang, is to do this in with a pulse laser. So all of those examples I've shown you so far were done with a continuous wave laser, but we've actually modified the system to work with a pulse laser, a 1040 nanometer chromacity fiber laser, which can output a number of watts of average power. We can send that through a nonlinear crystal, split up the different wavelengths, put them back together, and send them back to a detector. Here, our signal is being detected around 1535 nanometers, and our idler around 3.2 microns. This is the detected signal, and now the detected signal is so bright that we don't need any single photon detectors or highly sensitive. Well, we need a highly sensitive detector. We don't need single photon detectors. We just use this amplified photodiode with variable gain in order to detect the telecom band output. And we're able to see that in a normal parametric down conversion system, you would only get a linear increase of signal as you increase the pump power. But as you approach this high gain regime, you get a self-stimulation in the nonlinear crystal. That means you get an exponential increase in the amount of light that you can detect. And we have a parametric gain here of order 4. Why would we want to increase the gain in this nonlinear interferometer? Well, it turns out that for a fixed, if you have a different kind of loss, a transmission of your idler, which is your infrared wavelength in your system, then it turns out as you increase the gain, you can increase the visibility that you have in the system. So this is an example of us introducing different losses into the idler in terms of optical density, or these are ND filters. And for no ND filter, we see as we increase the gain, we get an increase in the visibility, and it saturates. But as we increase the loss, you can see that the visibility gets really, really low for these low gain regimes, but can be improved by increasing the gain in the system. So if you have a very lossy medium that you want to image through, then it's better to have a high gain system. You can also introduce an extra loss on the detected arm inside the interferometer, so the detection wavelength inside the interferometer. And this can then allow you to increase the visibility even further, even in the presence of loss. So you can maximize the interference visibility. So we decided to turn this into an imaging system. So we placed our high numerical aperture zinc selenide lens into the idler arm, and we used stepper motors to translate a sample that was made of gold that had been etched away in various places. So this is a picture, for people that don't know, of Gromit from Wallace and Gromit. We then moved our sample through the focal point of the mid-infrared light, but only ever detected the 1535 nanometer photodiode signal and recorded the interference visibility at each position. This allows us to reconstruct a high visibility, high resolution image of this on-off target in our interferometer. And this is just an example of similarly scanning our QuSIT Labs logo that was on the same sample. So now we can do sample scanning microscopy at mid-wave infrared wavelengths, high gain, so we can be not susceptible to losses, with a very close to diffraction limited spot in our microscope. Another way to increase the light that you can have in the interferometer is, instead of using a spontaneous parametric down conversion process, you can seed the process by sending in a seed laser at the wavelength that you want to probe a sample at. So this is an example of pumping at 532 nanometers, detecting 810, and seeding at 1550 nanometers. With no seed, we have a very low contrast, but as we increase the seed level, then we can see a linear increase. We can get much, much higher, so hundreds of times increase in the contrast, and we also see an improvement in the visibility of the nonlinear interference as we seed the system. It's exactly the seeding process that we've used here in Bristol to perform nonlinear interferometry for gas sensing. Here we pump at 671 nanometers and have a seed laser at 3.2 microns, and that's targeting methane detection. Methane, strong greenhouse gas, and also very important for the oil and gas industry for detecting leaks and other things. If we pass those two wavelengths, 671 and 3220, through a nonlinear crystal, we can generate 848 nanometers. The infrared can pass through the gas, and the pump all comes back to the nonlinear crystal. We reflect all of the light back through the same nonlinear crystal, and we're able to generate signal light on the second pass. By tilting this mirror in the interferometer, we have a phase shift that's spatially varying across the beam, and that means that when the two signal beams interfere at this CMOS camera, then we get vertical fringes from one shot, and the visibility of those fringes tell us about the density of the gas that's present in the idler arm. This is an example of those fringes when our seed laser is tuned on and off resonance with the methane, and you can see you get a reduction in the fringes when you move on resonance. And the visibility of that tells you about the transmission of the gas. By tuning our laser wavelength, we can step the laser through the methane absorption, and we can measure that transmission for every wavelength step. And what we see is the spectrum of methane. This matches the HyTran database. We have a very small spectral step size that we can employ. This is in wave numbers around 0.0056. This is about 1 gigahertz of frequency resolution, if you prefer. And this detects with good accuracy a gas cell in our interferometer. And only 0.2 milliseconds per measurement needed because of the fast CMOS camera that we're using for detection. If we scan the laser wavelength further, we can also see the water vapor in the room, and this matches very well to a commercial hygrometer. But actually, this is the case for not transmitting just through a cell, but we extended the distance of the sensing arm to 22 meters, so 11 meters in the lab, double passed. And this meant we could detect the background level of methane that's in the room, which is only 3 parts per million. Minimum detectable change of around 140 parts per billion. And this 22 must be greater than 22 meters mutual coherence length between the 2 lasers that we're using, means that we know that we have lasers that are of order a few megahertz in line width, which is very good. That means eventually we could have even resolutions for this technique that are down at the megahertz level. We also asked ourselves the question of whether we actually needed a mirror at the end of the interferometer. It turns out we can actually replace the mirror with anything we like, a piece of paper or anything. And as long as we collect enough light using a lens on the way back, then we're able to also detect methane using a Lambertian backscatterer. So we were able to still see the methane cell by performing this technique, but it came with other advantages. If you have these lenses inside your interferometer and a Lambertian scatterer, then the angle that you set the scatterer at means that you can collect light for very many angles of your target. If you had a mirror here, it would just be a straight beam, and the beam would not come back to the same point. But because we have a Lambertian scatterer, we can change the angle of the target and still see high visibility for many angles, whereas a mirror, we would see a reduction in visibility after only just a few degrees of detuning of the mirror. We were able to detect methane over around 4.6 meters distance, so the background methane in the room. There's not very much methane within 4 meters or a few meters, 1.4, 3.1, and 4.6 meters, hence the low visibility of the methane spectra there. But we can extract the methane concentration with high accuracy by fitting to the HyTran data. Another thing to point out is actually as you extend the distance, the loss in the system scales as 1 on L squared, but actually the visibility scales as this function, which simplifies to 1 on L. So this means actually the visibility is only decreasing as 1 on the length. So it means you can operate over a longer distance. And this is a consequence of the system being sensitive to the amplitude of light rather than the intensity of the light. We also changed the target for different materials, a leaf, a piece of glass, brushed metal, and we were able to see the spectrum of methane by using all these different real-world targets. And this work's published in this APL photonics paper. Okay, I've spoken for a long time. However, I did want to just touch on some integrated photonics experiments because I'm in Bristol and it would be remiss of me not to before I finish. Do you mind if I just do that, Aurora?
Yeah, please go ahead.
Okay, very good. So as many of you will know, many quantum optics experiments back in the early 2000s looked like this large optical bench, and some quantum optics experiments still do. But many quantum optics experiments now can be miniaturized down onto integrated photonic devices, whether they be in different platforms such as silicon, silicon nitride, lithium niobate, to name a few. And this has enabled many advances in quantum computing, simulation, also networking, but also sensing. In 2019, Jonathan Matthews with John Rarity created an integrated photonic chip to perform this nonlinear interferometer process. So they had a beam splitter that then split the pump laser between 2 different nonlinear optical processes. In this case, it was a spontaneous 4F mixing process in silicon, and they were able to pass the signal photons and hydrophotons from the first process through the second process to build the interferometer. So this is what that looked like on an integrated photonic schematic. A Mach-Zehnder interferometer splits the pump light between two different sources that are spiral waveguides here. And asymmetric Mach-Zehnder interferometers are able to split off the pump light from the signal and idler photons, and the signal and idler photons are allowed to pass the second source before being split up and detected. This is all at telecommunication-band wavelengths. So they sent 10 milliwatts onto a chip, and each spiral was around 1.4 centimeters long. They generated around 100 photon pairs per second in this case. They were able to see nonlinear interference, so a modulation as they changed the phase on the chip, and they were also able to detect correlations and show that the correlated light was also able to perform sensing of that phase. However, the visibility here was quite limited by the losses that they had on the chip. So we've recently taken this idea and put it into an integrated photonic device, but this time we've extended the wavelength out to 3.2 microns, where we want to probe methane, and we're detecting telecommunication-band light. So how do we do that? How do we generate these broadly non-degenerate wavelengths on a chip? Well, it turns out if we pump a nonlinear optical waveguide, so just an integrated waveguide shown pink here, with two different modes, so a T0 and a T1 mode. So we have one photon of the pump on, well, we have the pump pulse on both modes. If we take one photon from each of those modes at 2 micron wavelength, then we're able to generate signal and idler that are now on two separate fundamental modes of the optical waveguide. And we can use what's called mode converters on the chip in order to convert modes between these different modes. So bring this onto the fundamental mode and back again, and vice versa. In doing this, this allows you to match create phase matching between these broadly different wavelengths and generate 1545 nanometers and 3.22 microns simultaneously. This is a picture of the chip here, and you can see it's been wire bonded onto a PCB, and then this is a picture of lensed fibers pointing at the edge of the chip to bring light on and off of the chip. As we scan a phase inside this interferometer, we're able to scan pump phase, signal phase, or idler phase, and we're able to see nonlinear interference on this integrated photonic chip. So here we're seeing that this is a much longer wavelength, so it's a longer period, pump and signal, and the pump, remember, is in the middle wavelength, hence having a broader period than the signal. So this is 2 microns, telecom, and 3.2 microns. We now need to introduce methane into here, but in the meantime, we had a Mach-Zehnder interferometer in the 3.2 micron arm, which allowed us to introduce a controlled amount of loss in the system. So by controlling the loss in that midwave infrared arm, we were able to modulate the visibility. So the visibility was changing in the output telecom detection. So here we're doing integrated sensing of midwave infrared wavelength loss by only detecting telecommunication-band light. Future work would be to take this kind of work and integrate homodyne detectors on the same device, and this was work that was started by Jonathan Matthews while he was here, with many of his impressive students and who were then postdocs who've now founded companies, where they integrated homodyne detectors on a chip, integrated electronics on a chip nearby, and then integrated everything onto a single chip. So optics, so integrated optics and integrated electronics simultaneously to create what's called a homodyne detector, a detector that can be sensitive, but while mixing with by mixing the signal light you want to detect with a local oscillator. We've taken this and we've integrated multiple detectors onto a single device. So this is Beth Peugeot's work, and she's been integrating 4 detectors on a single device. The device also has an array of beam splitters that allows us to share a local oscillator and an input mode with multiple integrated homodyne detectors. And if we do that, then we're able to detect a change in phase shift in each arm of this Mach-Zehnder interferometers of the homodyne detectors. If we send in coherent laser light, you can get an improved measurement of the average phase shift here, but that improved measurement is limited by the fact that you're using classical light here. If instead you send squeezed vacuum into this input, then you can create entanglement across these modes. And that entanglement across the modes can improve the accuracy with which you can detect this integrated average phase shift. So if you sent separate squeeze states through, you'd be able to be 0.074 dB below the shot noise limit. But if you use entangled states, you can be 0.2 dB below the shock noise limit for the current experiment. And this could be improved with a higher level of input squeezing, for example. Another thing that we've recently done, and this is Ollie Green's work, is to take an integrated photonic chip and an integrated and a local transimpedance amplifier, bond them together. The integrated chip now contains a spiral waveguide to generate squeezing and an integrated homodyne detector, so 2 photodiodes balanced in a beam splitter in order to detect squeezing, and put the whole thing inside a Faraday cage with a coupling setup. So this is a schematic of that chip. If we send in 2 pumps simultaneously into this chip, we can do what's called a dual pump 4-wave mixing process, where we generate squeezed vacuum at the center here of the two pulses of light. So at the average wavelength between them. We can then mix that with a local oscillator that's the same wavelength as the squeezing in a Mach-Zehnder interferometer and send that to our integrated homodyne detector. So we can create these wavelengths of light, the local oscillator and the 2 pumps, by carving with a wave shaper these 3 wavelengths out from a broadband pulse laser source, again at telecommunication-band wavelengths like we talked about at the beginning. We can send those different light pulses into the chip, and these asymmetric Mach-Zehnder interferometers are used to remove the pumps after they've done the generation that we want. So this is the final plot that we get as we change the phase shifter in the local oscillator. We can see that our variance goes below the shock noise limit for this integrated squeeze light that's generated and detected on the same device. And this is a plot of the squeezing and the anti-squeezing as you change the peak power coupling into the device. So this is the first directly observed sub-shock noise signal from silicon in an integrated photonic device. So, yeah, congratulations to Ollie for that. It's very impressive. That's everything I wanted to tell you about today. So lots of different telecommunication band quantum technologies, spanning 3 different quantum hubs, plus some extra integrated photonics sprinkled on top at the end. I hope you enjoyed it, and I'm very happy to take some questions from you. And thank you for hanging around. It was slightly longer than I planned, but I hope you had a good, interesting discussion.
That was very interesting. Thank you very much. That was great. There is a question on the last part in the Q&A section from Emma.
Very good.
Is there any expected difference in the resolution of the undetected photon setup when changing the process from SPDC to high gain or seeding the process? Maybe because of the different type of correlations involved?
Yes. So if you're doing the full field imaging, that is, you're using a camera to image the different modes from the down converter, then yes, as you increase the gain, you narrow down the modes that you generate and you decrease the number of modes that you have to image with. So you definitely get a decreased field of view and a decreased resolution. However, here, because we're doing sample scanning and we're only using a single mode that's focused, and then we're moving the sample through the mode, that means we don't see a change in the resolution. So we expect the resolution to remain very high. In fact, we may even see an improvement in resolution in the high gain case, because we're actually trying to use a single mode to image. So rather than selecting one mode from many, if we only have one mode to begin with, then we could have an improvement. So this is for the sample scanning. It's better. If you want to do full field imaging, like we showed earlier on with the electrodes and things in the continuous wave case, it might not be better. Yes, it may be worse in high gain. You're right.
Okay, that's great. Thank you. So if you have any other questions, please write them up in this section. And while we wait another minute for people to type up any potential question, I'll ask you a question. And I will go for the usual question that I ask to anyone who went through miniaturization of a system. So what was, because in this last part of your talk, you show a few photographs from a much larger system to a shoebox size demonstrator. So in that case, what was the main challenge in the miniaturization process that you went through?
Yeah, I think sometimes there are a lot of large electronics boxes that it seems like you have to have present in order to make your system work. So I think miniaturizing the electronics, it's doable, but it's something that often we might not do very well at the university, perhaps. It's good to have companies involved who can help with that. The interferometer itself can sometimes benefit from having a longer propagation length in the system. It can make it more sensitive, but it can also allow you to have more modes for your imaging. So because you can effectively allow the beam to expand into larger optics. So it may limit the field of view that you would have for a microscope by miniaturizing things further. I think the other difficulty, or what we didn't really try, and I think would be the next step for the kind of bulk optical miniaturization, is to have something that's more like a CNC aluminium block that really houses the mirrors more effectively. And actually, there was very recent work from Sven Ramelau's group, which Emma Pierce, who's now in Glasgow and does a lot of work in the hub now. She was part of this work that miniaturized a nonlinear interferometer down to something that's more like a cassette size. So, hang on a minute, it's probably young people here. About 10 centimeters by 10 centimeters or so in size. So very small. And that was because they basically milled out a piece of aluminium and they mounted all of their nonlinear crystal heaters, mirrors, optics inside that. So I think you could miniaturize these things further if you were willing to go down that kind of CNC route.
Okay, thank you. Well, my other question was about the length of the arms of the interferometer, but you already commented on that, so it's all good for me.
Sure.
And I see that there are no other questions in the section. So I will just move on, and thank you again very much for the fantastic presentation you delivered today. That was a really impressive work, and thank you to take the time to explain your work to us.
Thank you. No, thanks to everyone for their attention and for their time. And yeah, if you do have further questions, you can always catch me by email as well. Thank you.